So last time we did. We're happy for today, actually. That's great. Okay, page 88, please. Guys, come on. 88. Brandon. So, in this lesson, we're going to look at something called the second derivative. So far we've been dealing with what's called the first derivative. And the second derivative, not much different. In fact, it's nearly the same. A second derivative just means we calculate the derivative again. So for example, if I had y equals x4, what's the derivative here? Well, that's 4x cubed, yeah. The second derivative is literally the derivative again. So we just do it again. Yeah, so what would that be? 12x squared. So there's nothing more to say about it than that. What's more important is what does the second derivative represent? So the first derivative, what is the first derivative? What does that represent? The slope of the tangent. Yeah. The second derivative, what does that represent? So that's what we're going to have a look at today. Secant? No, not that. What about Omar? Are you speaking Arabic?
No, I'm speaking Urdu.
Why are you speaking when I'm teaching here? What's the question?
I'm asking if the second derivative is still for the slope.
You can ask me that.
So you did.
Yeah, I get paid to teach you. Ugo doesn't, alright? Well, you know what you need to do. You put up your hand then, and then patiently wait. I mean, you've been a student before. You know how these things work. Okay, so the second derivative, yes, it's almost like a slope. But what exactly does that mean, slope to slope? So, if you want, you can think about it. One way to think about it is like this. Here's x, here's y, and then you draw your graph, and the first derivative is this. Now, you could make a second graph, where here is x, and then here is the value of the derivative. So for example, here, the slope, what is it, positive, negative, or zero? Positive. And then as I go up, what's happening to the slope? It's what? Decreasing. And then when it's up here? At the top? Zero. And then here? Negative. Decreasing. So, if you were to plot that, you would get a graph, something like this. Or if it was a bit of a curve, it might be, I don't know, something like this. Positive, zero, negative. So here, look, let's imagine that this happened, the maximum at 3. Then this point here would be 3, because this is where the derivative is 0. So then the second derivative will be the slope of to the tangent of this graph. Now, some people can see that, some people can't, and it's okay if you can't, because there's a second way to view the second derivative. So if I scroll down, the second derivative tells us something about the shape of the curve. So for example, we can know if the curve has a shape like it to this, or a shape like this to it. This is called concave, and this one here is called convex. Now in fact, the only example of this we've seen so far is with the quadratic. We know if a quadratic has a positive x squared, it's convex. Yes, very good. And if it has a negative x squared, it is concave. Now look at what you get for the second derivative. What's the derivative here? Well, it's 2x plus 1. And then what's the second derivative? It's 2. Now, if I was to change this to a minus, what would be the only difference in my answer here? Negative. So in fact, the second derivative, if it is positive, or if it's negative, it can tell us if we have a concave type of shape or if a convex type of shape. So in other words, this type of shape happens when the second derivative is negative, and this shape happens when the second derivative is positive. I am recording this, aren't I? Yes. So I'm sorry, the reason for the colours here is, firstly I did it without the negative, and then I did it with the negative. Now this can be very useful for finding the maximum and the minimum points. And I'll do an example of how this is useful now. So I need something, I'll need to do an example with like a cubic. So we'll just make a cubic first. Okay, can I scroll down? Yeah. So we want to find the maximum and minimum points to this curve. Y equals x cubed plus, I'll have to wait. No, not there yet. Getting there. Getting there. Come on, open up. I did pick it. I don't want to think of one. There we go. Good, no thinking. That's bad. Okay, so let's see. Let's say x minus 2, x minus 4, and expand. Okay, so let's use this cubic. X cubed minus 6x squared plus 8x. X cubed minus 6x squared plus 8x. So x cubed minus 6x squared plus 8x. What I want to find are the minimum and maximum points. So we know what to do here. We first calculate the derivative. So that is a 3x squared minus 12x plus 8. Then what do we do with that? No, before that, what did we do last time? What do we do with this answer? Yeah, because what does it equal? Equals 0. So I think this has factors. I mean, I don't know. Let's see. But it has to be a 3x. It has to be an x. It has to be a minus and a minus. 4 and 2 wouldn't do it. No, it would actually. 2 and a 4 here. Would that do it? 3x squared plus 8x minus 6x. No, that's a 10. Does it have factors? Firstly, can you check in your... It doesn't. Okay, so we'll just have to use the formula. So x equals minus b plus or minus the square root of b squared minus 4ac minus 4a 12, sorry, b squared minus 4ac. 12 times 8 is 96. All over 6. So x equals 12 plus or minus the square root of 48 all over 6. X equals 12 plus or minus the square root of 4 times 12. But 12 is 4 times 3. This is, sorry, this is, hold on. Just let me think about 48 for a second here. It is 4 times 12, isn't it? And 12 is 4 times 3. So this... Yes, that's what... Yes, I'm just doing this without a calculator. But thank you for your help. 4 root 3 all over 6. So x equals 2 plus or minus 2 over 3 root 3. So please tell me what these are in decimals, because I cannot do that without a calculator. What's the first one?
3.15.
3.15? And the second one?
845.
Okay. Now, we know how to find the y values, so we won't bother to find them just to save time, but we know how to find the y values. How do you find the y values? You substitute it back in at the start. But here's the big question now. How can we tell which point here is giving me the maximum and which is giving me the minimum? We just know these are the turning points, but we don't know if it turns to a max or a min. Like, for example, we don't know if it's like this, and the first point here is a max, and then the second point is a min, or maybe it's the other way around. Maybe this first point is a min, and the second one is a max. We don't know. But what we can do to check is we can check the second derivative. What's the second derivative here? 6x minus 12. So if I calculate the second derivative, that's 6x minus 12. Now, if I put this value of x in, do I get a positive or a negative answer? You'll get a positive. I mean, you can work it out on your calculator, but I can see it's going to be a positive. It's going to be roughly 18 minus 12. So it's going to be a positive. Now, what happens when you put this value into the second derivative?
Negative.
It'll be a negative. So you know that at this location, is it concave or convex if it's a positive here? What do we say? Convex, yeah. So we know at the point 3.15 we have a convex shape. And then it's negative later at, oh sorry, let's draw this properly. There's 0, there's 0.845, and there's 3.15. So at 0.845 it's negative, which is concave, so it's this kind of shape. And then at 3.15 it's positive, which is convex. So the graph is actually, let's try that neatly. The graph is like this. So the first answer, is this a max or a min? This one. Max. And you can tell because the second derivative is negative. This one here, the minimum. And you can tell because the second derivative is positive. In other words, if you want to know if you have the positive or the if you want to know if you have the maximum or minimum, you just need to know if the second derivative is positive or negative at that point. So, to summarize this idea, if the second derivative is positive, we have a min, and if the second derivative is a negative, we have a max. Now please note, these are probably what's called local min and local max, because if you think about it, is this point really the maximum point on the graph? Is it the highest point on the graph? No, because what's happening? This is going up to infinity. So it's not really the max, but it is the maximum locally. You know, if you just look at this piece, it's the maximum. But it's not the global, it's not the overall maximum. So it is useful to put these words local in front. You're making the point that locally it's the maximum, and here, is this the minimum? Globally? I mean, is this the minimum? No, because what's happening on the left, it's still going down to minus infinity. So it's a minimum, but it's only a minimum in, you know, the small part of the graph here that you can see. So that's why I put these words local and local here. So we can use one application of the second derivative is to tell us if we have a maximum or if we have a minimum. Another application is to tell us if we have a concave shape or if we have a convex shape. Let me give you an example here. Can I scroll down? Yeah. So this is our sine graph, and we're using radians. So I have y equals sine x. And what's the derivative here? Cos x. And what's the second derivative? Minus sine x. Now in your calculator on radian mode, I want you to type in into the second derivative. Let's see, here is pi over 2. So I'd like you to type in pi over 4. The answer should be negative. So what do you get?
Minus 0.7.
Yeah. Now the reason I know that it should be negative is because what shape is the sine graph here? Concave. So no matter what value of x I put in here, it's concave shape, so it should be negative. But what about if I pick a number over here? What shape is the graph over here? Convex. So convex, the second derivative should be positive. So why don't you try putting in, let's see, put in the number 6. That's about there. There's about 6. It's positive. And what about if you put in 5? It's positive, isn't it? Yes. What about if you put in 4? It's positive. So all the numbers here give you a positive second derivative. That's because the shape here is convex. But what about right here? Is the graph convex or concave here at this piece?
No.
Concave. But it's
Maybe not. Yeah, so why don't you put in pi into this and see if it's positive or negative? So that 0 second derivative has a meaning as well. If the second derivative is 0, it means the graph is switching between being a concave graph and being a convex graph. It's like it's switching between the two shapes. That's the meaning of the 0 for the second derivative. So I'll just summarize that down here. Can I scroll down? Yeah? Now, this point has a special name. The point when it switches from being concave to being convex or vice versa, this point here is called the inflection point. Okay, can I scroll down? Yeah, so actually before I summarize this, I want to give you another example of concave and convex. So we'll use the same cubic we had earlier. Y equals x cubed minus 6x squared plus 8x. So my question here is, where is this concave? So I want to know where on the graph this will be concave. So how might I do this? What might I need to solve? Second derivative, what about the second derivative? What do I want it to be if I want it to be concave? It should be, yes, negative. So in other words, I need to solve this equation. Negative. So what's the first derivative here? 3x squared minus 12x. And then therefore, what's the second derivative? Plus 8, thank you. And what's the second derivative here?
6x minus 12.
Yeah. So I want the second derivative to be negative. So that means x needs to be smaller than 2. Because this will be 12 over 6. So what do you think would happen if x was bigger than 2? What shape would that be? Convex, yeah. So if you can imagine it, you're thinking it should be concave, and then it switches to being convex round about here at 2. It should be concave as long as x is less than 2, and then if it's not less than 2, then it's probably going to be convex then. So if I graph this, what I would really like to see is the switch happening at 2. So let's graph it. Oh, beautiful. So you can see that it's concave, and then what happens when it hits the 2? It switches to being convex. Exactly as predicted. So we have many, many ideas here. So I'm going to summarize all these ideas in a table, which is actually, some people, that's what I asked you to do in the last question, which some people have. How many people have that table at the bottom of the book? There should be a question with a table in it. Some people do have it, some people don't. Doesn't matter if you have it or if you don't have it, because I'm going to make that table now. Okay, so we have here. So we could have the first derivative is positive, the first derivative is negative, the first derivative is 0. And also the second derivative is positive, the second derivative is negative, and then the second derivative is 0. I think maybe I wrote it a little differently in your book, it doesn't matter. Just copy this down. So we'll try and fill this table in together. What I want to put in each box is all the different shapes we can get. So the first box, the first derivative is positive. What does the first derivative represent? The slope of the tangent. So if it's positive, what's happening? It's increasing. What does the second derivative represent? Yeah, the second derivative, what does it represent? If it is concave or convex. So it represents what's called the concavity. So if the concavity is positive, what shape is that? Convex. So it is increasing and it is convex. So if it's increasing and it's convex, that must mean we have this type of shape. It's increasing and it's convex. Do you see what I mean by the convex shape? But it's increasing. So it's like it's going from a low point to a high point, and it's bulging out. Now, in this graph here, the only difference, it's still convex, but now the second derivative the first derivative is negative. So it's decreasing, but it's still convex. So I should still do it bulging kind of outwards, but it's decreasing. There we go. Like this. I'll draw that a little nicer. Okay. If the first derivative is 0, what does that mean? If the first derivative is 0, It's flat. But it is also convex. No, not that one. You're thinking of down here. Oh, which should be have this. This one here, if the first derivative is 0, that's a turning point. And if the second derivative is positive, that means it's a minimum. It's at the bottom of like a hill. So the graph is flat. We're talking about really just this point here. The point where the graph is flat at the bottom of a hill. And this one here we're talking about like here, and this one here we're talking about all up here. But in this case we're really only talking about the point at the bottom. Now, the only difference with this situation is that instead of being concave, it's convex. So, in other words, it's still increasing, but it's increasing convexly, so it's like this. This one here is decreasing, but it's decreasing convexly, so it's like this, like this. And this one here, again, is now going to be flat, but at the top of a hill, so we're talking about like this point here. This one's concave. Sorry, have I been saying convex for this one? So sorry. Concave, and this one is convex. Okay, now this is where it gets a bit more complicated. The second derivative is 0, but the first derivative is positive. So if the first derivative is positive, what is it doing? It's increasing, so it's increasing. But if the second derivative is 0, what does that mean? It's switching. Yes. So we have to draw this increasing, but switching between a concave or a convex. So we have two choices. We can draw it like this, or we can kind of draw it like this. Now in this case, going from concave to convex, can you see that it's going down? Yes. Whereas in this case, going from convex to concave, it's rising. So which of the two do you think it is here? It's the second one. So I'll just draw the second one in here. No, that's the wrong one. So we're talking about here, this part of the graph, really this point actually. This one's really just a point, this one here is really just a point, Okay, this one here is the other case that I didn't look at a moment ago, so that's like this. No, I'm drawing the same thing. So again, it's really just this point, this switching point here, this inflection point here. The last one, the first derivative is 0 and the second derivative is 0.
Yeah, so it's
So we think it's flat and changing.
No, not change. 0,
Who
0,
knows?
0.
Who knows? What do we know? Blank. The problem is when the first and the second derivative is 0, in fact it's not clear what we have, really. It is probably, but not always, it's probably something kind of like this shape, where it's concave, flattens, and then goes convex. Now, I'm saying probably, it's definitely not always this. So in the exam you couldn't just say, oh, it's this shape here. I'm just saying it's probably something like this, because here it is concave, yes? And here it is convex. So here what's it doing? It's switching between the two. So that means the second derivative is 0. Yes? But what's the slope of the tangent here? 0, because it's flat. Now, don't think it's always this. There are definitely times when it's not this. I'm just saying it's probably this. And this situation has a very special name. It's called a saddle point. That's the name of it. Saddle point, yeah. Saddle, like horse saddle. So it's called a saddle point. But it's very important that you write this big question mark in here and write maybe. Now there is, what I'm going to show you now is there is a way to check if it is this or not. So we'll call this one a saddle point. Maybe. And for goodness sake, make sure you make the maybe very clear, because I'm not saying it is. So, how can we check if we have a saddle point? That's what I'm doing next. Can I scroll down from this table? Yep. So the check for saddle point. So if it's a saddle point, you need three things to be true, really. Number one, if you didn't write it in on your table, I think it's a good idea if you write here inflection, and then what are these two called? No. Stationary, these 2 points. Stationary points. So actually write them in, please, if you didn't. What's wrong? Okay, can I scroll down? Yeah. So in the situation when the first derivative equals 0 and the second derivative equals 0, you may have a saddle point. If this happens, you need to check if you have it. So there's one more thing to check. It's a saddle point. Let me just say, by the way, that this is at, let's call the point x0, whatever point it is. So it's a saddle point if y, x0 minus a very, very small number is a different, is smaller than x0, oh, goodness sake, sorry, is smaller than y x0, which is smaller than y x0 plus a very small number. Or the opposite, you could have it the other way around, with a bigger. And note, please, you can use any small number, e.g. 0.0001. So what you're really doing here is you're looking a little to the left and you're looking a little to the right, and you're seeing if the graph is going up on the right and going down on the left, or the other way around is fine. So let's have a look at an example where we do have a saddle point. Okay, I can scroll down? Yeah. I'm scrolling down. So here's my example, y equals x cubed. I would like to find the turning point. So firstly I calculate the first derivative. What's the first derivative here? 3x squared. And if this equals 0, what does x equal? What's x here? 0. And if I put x back in here, what's y? 0. Now I would like to know what type of turning point this is. Is it a maximum? Is it a minimum? Is it a saddle point? So I calculate the second derivative. What's the second derivative here? 6x. Now if I use x as 0, what do I get here? 0. So the first derivative is 0 and the second derivative is 0. So we could have a saddle point. We need to check. So the way we check is we put in x minus a small number. So what's my value of x? 0. So if I just make minus a very, very small number, then it would be minus 0.0001. All I'm doing is I'm moving a little bit to the left. Cubed. Now what's the value of y?
It's minus.
0. So that's 0. And then I want to check if this is smaller than when I move a little bit to the right. So if I add a very small number to x, what do I get? It would be something like 0.0001 cubed. So all I'm doing is I'm using h as 0.0001, and I'm adding it to the x, and I'm subtracting it from the x, and I'm using those two numbers back in here. And this 0 is just because of the y, it's not because of the x. They're just both 0 here. So is this true? Is this number smaller than 0, and is 0 smaller than this number?
Yeah.
It's true. So then we do have a saddle point. So the shape should look something like this. Well, let me surprise you. So x cubed. Oh, look at that. So it is a saddle point. Goes concave, flat, convex. So let's have a look at some examples from the book here. Okay, perfect. But I better plug this in before I lose everything. That'd be bad. Okay, so what I'll do is let's have a look at 1a, 2a, 3a, and 9. 1a, 2a, 3a, and 9. So firstly 1a. Very, very short question. So I would like the second derivative of 5x cubed. What's the first derivative? 15x squared. And so what's the second derivative? 30x. So you're finished. 30x is the answer. That was 1a. Let's have a look at 2a next. Find the stationary point and determine the nature of it. In other words, find the stationary point and say if it is a maximum, a minimum, or a saddle point. Okay. So if I want the stationary point, I need to calculate the derivative. What's the derivative here? Minus 2x minus 14 equals 0. So then x equals minus 7. Can somebody please put that back in here and get me the y? You know what? Don't bother, it's okay. It's 45. Now we need to know if it's a max or a min, but we kind of already know the answer because what shape is minus x squared?
Concave.
Concave, so it should be a max or min? Max. But we still in the exam need to prove this. So the second derivative is equal to minus 2. Minus 2 is less than 0. It's a negative number. This means it is a concave shape. Therefore, minus 745 is a max. Now, interestingly, is this a local max or is it a global max? In other words, is it the maximum everywhere or just locally? Everywhere. Is there any point on this graph which is higher than this? No. Sorry, I feel like I'm boring you over here. If you look at this, is there any place where the graph is higher than this? Hey, at least I have one person who's interested. Is there any point higher than this? No. Now you said it's a local max. Yes, true. It's still local max. It's still the maximum in this kind of neighborhood. But if I was to look at the whole graph from minus infinity to infinity, is there any place higher than this? No. So in fact it's also a global max as well. But don't worry, either way it's a maximum. I'm just saying we know it's a global max as well, not just a local max. Now, they have never in the past asked for this, so I don't think they will. They just would like it to say if it is a maximum or a minimum. I'm just saying it's a global max in this case. Right. Number 3. Can I go down? Yes. So number 3, I actually did one just like it earlier. I want to know where is this function concave. So what's the first derivative here? Well, that's 9x squared minus 18x plus 6. And the second derivative? 18x minus 18. And if I wanted to be concave, then I want this to be negative. So then what do I know about x? Should be, yeah, if I solve this, what do I get? Less than, no, solve it in your head. Come on, what's that? Less than 1. 1? Yes. So, x should be less than 1. Another way of saying that is x should be from minus infinity to 1. And that's the answer for that. Okay. Can I scroll down? Not sure. Okay. Yes, no, I need to scroll down. This will be the last example.
Global maximum that one is 1.
No, I'm just saying it's concave as long as x is less than 1. Where is the inflection point for this? So if I want the inflection point, what's special about the inflection point?
0.
Let me turn my alarm off so it doesn't bother anyone. Second derivative needs to be 0. So we have the first derivative, what's that? 9x squared plus 18x minus 7. And what's the second derivative here? 18x plus 18. I want this to equal 0. So then what does x equal? Minus 1. Now is that finished? No, I still need to get the y. Oh no, I don't. I think I just want the x for these ones. What number is this? Sorry. It is 5. Which for some reason I don't have. It's cut off the page. What do you mean you don't have 5? I'm looking at it right here. It might just be numbered differently. Let me have a look at yours. Hold on. 5 in this book is actually where?
3C.
3C. This is 3C. Is it?
Yes.
Yeah, minus 1 is the answer at the back. This is not finished though. It's not finished. It's not finished because if we go back to our table, the one I drew earlier, zoom in. Oh, for goodness sake. Here, table. There are two situations where you get an inflection point. When the second derivative is 0 and the first derivative is positive, or if the second derivative is 0 and the first derivative is negative. But in this situation, do we have an inflection point?
No.
No, maybe. We don't know. It's not clear, okay? So we just need to make sure that our first derivative is not 0 when x is, what do we get? Minus 1. So just put minus 1 into the first derivative and tell me what you get. So if I put minus 1 in here, I get 9 minus 18 minus 7. Well, I can see that's not 0. So it's fine. It is an inflection point. Is it positive or negative, this first derivative? Negative. So is it increasing or decreasing? So it's a decreasing inflection point, so it will look like this. Now there's lots and lots and lots in this lesson, so you really need to practice them. Now I realise people have two different versions here. That would be one easy way to fix it, wouldn't it? So, firstly, both people have question 1 and 2 in both versions of the book. Some people have the table at the bottom and some people don't. Doesn't matter. Everybody should do question 1 because they're really short. Do all the questions in one. In number 2, it's enough to do the last 4. In number 2, Omar, it is enough to do the last 4. Please don't talk when I'm talking. So mark off the last 4 there. Now, for people who do have number 3 of A, B, C, D, E, F, G, etc., I would like you to do, one of each type. So you can see that there's 3B, which the other people, that's actually number 4. Yeah, do have the second question. So people do 3B, 3D, 3F, 3H, do every second question. And likewise the people with the other book do every second question. 4, 6, 8, 10, 12, 14, 16. So do half. In other words, after question 2, do half of what's left on the page. So do all of 1, the last 4 in 2, and then half of what's left on the page.
And what about 4?
Is 4 the table? I did that one. My table I drew in so it doesn't matter, forget about that. I'm not good against you though. Yeah. See if you can remember everything in it. Alright. 1, 2, 3, 4, 5, 6, 7, 8. So I'm missing, of course, Young, Saeed is gone, and Precious is not here either. Alright, get out here.